Hi guys and welcome back. So this is again on topic 4, looking at electrolysis. It's really the last little bit on electrolysis. It's required practical, the electrolysis required practical. If you were studying separate sciences, so triple science, it's chemistry required practical 3. If you're studying trilogy or the combined, as it used to be known, so you're doing the double award science, then it's required practical 9. And what we're learning about today is how to create a hypothesis, how to create a risk assessment, how to set up the electrolysis investigation, and how we test the gases to prove our hypothesis. And first step then is how to create a hypothesis. Now firstly, a hypothesis is an explanation for what you think is going to happen as a starting point for an investigation. This is often confused in everyday terms, in everyday language, by people out and about as a theory. So a lot of the time people say, my theory is this is what's going on with person X, Y or Z. Well, actually what they mean is this is my hypothesis, or sometimes even my conjecture, which is something that's got even less of a basis in fact. But a hypothesis is an explanation for what you think is going to happen. An example: black cats are going to catch more mice at night compared to other kinds of cats because they're going to be harder to see in the shadows. That's an example of a hypothesis. That isn't a theory yet. Until I've proven it, until I've done the work into it and researched it, it is not a theory. A theory is something that's got a substantial body of evidence behind it and can be tested repeatedly and comes up with the correct real world solutions. So for example, the theory of gravity tells us things fall towards the center of an object of mass, and we can see that happening every day. If you take a pen or a ball now and chuck it up into the air, the pen or the ball will inevitably fall down towards the earth, and we can even predict at how fast it will fall and indeed how much force it will have when it hits the ground. We can mathematically predict those things incredibly well. So it's a theory, and what we mean by a theory there is it's something that's got a proof. A hypothesis is what you think is going to happen and you have to test it. We need to make a hypothesis, but firstly we need to have a look at the required practical. Okay, so what we need from the required practical is how to set up, perform and record results from an electrolysis of an aqueous solution. We need to be able to do all of that, and this is really important because it is something that will be examined or could be examined. So unfortunately at the moment we can't be in labs to do this work, but it is very important you put the effort in and make sure you know how to do this experiment and what kind of results you might expect, because you could be examined on it. Now, some commonly used electrolytes are sodium chloride, copper chloride and copper sulphate, and we're going to have a little brief look at those, but we should be able to figure out and predict what they're going to make from our last lesson. Okay, so this will form your hypothesis. You will say, I think that in the electrolysis of sodium chloride at the positive electrode we will make whatever you think you'll make, and at the negative electrode we will make whatever you think you're going to make. And this is going to be the basis of your hypothesis. You should be able to create a hypothesis of your own based on that. Okay, and you should also be able to assess what the risks are and suggest some ways of minimizing those risks. Obviously we need to keep this specific to the experiment, not just glass might break, because that's something we should be doing always, but it's things like looking at the chemicals and the dangers they might present. So your hypothesis should be based upon your knowledge of the electrolysis of aqueous solutions, which we looked at last lesson. You can find the video as well. I'll try and put it in the links, but if you've not watched it, but you can also search through my videos in topic 4 and it's in one of those. You need to say what you expect to see at each electrode and why you expect to see it. You need to use a scientific reasoning to explain why. Okay, your scientific knowledge needs to go into explaining why you're going to see what you're going to see. So things like the opposites attract. So an example for aqueous sodium chloride. The metal, sodium, is more reactive than hydrogen, so you'd expect to see hydrogen gas at the negative electrode. So you would say I would expect to see, for my hypothesis, I would expect to see hydrogen gas at the negative electrode because, and then explain why sodium is more reactive than hydrogen, therefore talk about the movement of the ions. Chloride is a halide, so we expect to see chlorine gas at the positive electrode. Okay, and again you can explain why, that the OH will be left behind, the chlorine gas will take the give away its electrons, or the chloride ion, sorry, will give away its electrons and become chlorine gas. And then sodium and hydroxide remain in solution and make an alkali. If we were going to do a hypothesis for copper chloride, it's slightly different. Okay, this time the metal copper is less reactive than hydrogen, and because it's less reactive, we're going to expect to see copper metal being formed at the negative electrode. But we've still got chloride as a halide, so we're still going to expect to see chlorine gas. If we use aqueous copper sulphate, we're going to see copper again at the negative electrode because it's less reactive than hydrogen. But this time, because we don't have a halide, we're going to see oxygen gas at the positive electrode. We'll also make water, but we're not going to see that in solution, are we? I mean, if you think about it, if someone's sneakily adding some water to your glass of water, you're not going to notice any difference. So, the experiment. We need a way of capturing the gases ideally so we can test to see what they are. Now this is very difficult to do in a school, and I'll talk about that in a minute, but we'll look at an idealized way of doing it. You also need a setup that's safe and allows for electrolysis to happen. So the equipment you're going to have unreactive electrodes, either carbon, most likely in school, or platinum. Now, the advantage of platinum is you can bend it into shapes, and that allows you to capture gases from it inside test tubes very, very easily. You can probably think of some of the disadvantages of platinum. Mostly it's expensive, and you can imagine that a school would not be particularly keen in buying quite a lot of platinum and then giving it out to people to do scientific experiments with. If you think about some of the ways that crocodile clips accidentally get lost sometimes, you can imagine a platinum electrode might go walking even more worryingly for the teacher. You're going to need a DC power supply. DC stands for direct current. It's no good having AC power supply. In this case, it has to be DC. You're going to have a beaker, an electrolysis vessel. So yeah, it could be either a big trough, it could be a small beaker, big beaker. Doesn't have to be glass, it could be plastic, doesn't matter too much. You're going to need wires, obviously, to connect up the power supply with your electrodes. And then you're going to need your aqueous electrolyte solution to perform your electrolysis on. That's the basics of the equipment. We'll talk about some more later. Now, risk assessments. They need to cover the major hazards and ways that you can minimize those risks, so lessen the chance of them happening. I think it's easiest to use it use a table and set it out as a table. And for GCSE, all you need to have is your risk, so what is going to be causing your risk, and your control, how you can control that or minimize it. So there's obvious ones like splashing things in your eyes or chemicals get in your eyes. Wear goggles is a control. Another example is you might get an electric shock. So to avoid that, we can use a lower voltage. Chlorine gas is also toxic, so you might want to perform it in a well ventilated area, so there's less chance of chlorine gas building up and causing breathing problems, and only run the power for a limited time, so you're not going to be producing loads and loads of chlorine. Now, the setup. In an ideal world, what you will do is you'll have some platinum electrodes and you'll actually bend these so you can get a test tube over the top of them without interfering with the wires connected to the power supply. So in that ideal world, we're going to have the test tubes, you're going to fill them with the electrolyte solution, you're going to put your thumb over the top and stick them upside down into this liquid and then put them over the electrodes, and that way it will trap the liquid in them. You can see bubbles of gas here. You're always in these experiments at the anode, you're going to get gas bubbles. You may also get them at the cathode, but it depends on what you're doing. So bubbles of gas are going to come up. They'll rise up and they'll push the liquid out of the test tube and gradually fill up the test tube with gas, and that's a good way of capturing it. So your method for the ideal world would be clean the surfaces of the inert electrodes with a fine sandpaper, also known as emery paper, and that's going to remove impurities that might affect your results. Then you're going to fill your beaker with your electrolyte and you're going to pop your electrodes into it. Then you're going to invert your test tubes and place them over the electrodes so they can capture the gas. Select 4 volts on the power supply because we don't want too high a voltage because it could be dangerous. Turn it on. And then we're going to observe until the test tubes are full. So we're going to observe what happens to the colour of the solution, to the amount of bubbles at each electrode or anything else that we may see. When the test tubes are full, we can stick off the power and test the gases made and check to see if there's any metal at the cathode being the negative electrode. However, because we are very, very unlikely to be using platinum electrodes at school, more likely method is what you're going to do is, again, step 1 is exactly the same. You can clean your electrodes, clean those carbon electrodes with very, very fine sandpaper. The second step is exactly the same as well. Fill the beaker or the vessel with electrolyte and place the electrodes into it. However, we're no longer going to invert the test tubes over the top because it's going to be extremely difficult, if not impossible, to actually get the power supply running into the electrodes. It's not impossible, but it's very, very difficult to do with school equipment. We're going to leave it running for 5 minutes, and if we think chlorine is going to be produced, we can test the gas that's bubbling up off the anode for chlorine gas. Now, if we suspect it's not chlorine gas, but we suspect it's oxygen instead, that is going to be significantly more difficult to deal with unless we can concentrate it somehow. What we can do, though, is very easily visual check to see if there's any metal deposited at the cathode. We can also see if the solution changes colour, which it may well do. Now, you are expected to note the test for 3 common gases, and you are expected to know not just what the name of the test is, but how to perform it. So the 3 tests you will need to know are the test for hydrogen, also known as the Squeaky pop test, the test for chlorine, which is done with damp litmus paper, and the test for oxygen, which is relighting of a glowing splint. Now, you need to know it in a bit more detail than just here, so we're going to break it down to each individual test now. So for hydrogen, the Squeaky pop test. First, if you collect the gas that you think is hydrogen, seal the test tube with a bung, then go and get yourself a splint, light it, then remove the bung and insert the lit splint into the test tube. If it is hydrogen in there, you'll get a squeaky pop sound, which sounds a little bit like, and I hope the microphone can pick this up well enough, it sounds a bit like whoop, a kind of a high-pitched noise like that. And that is characteristic for hydrogen. What's happening there is the hydrogen's reacting with the oxygen, and the reaction is explosive, and the gases that are being produced, or the water vapor that's being produced, is very, very hot, and it causes the gases inside the test tube to expand and rush out, and it makes that whooping noise, or the squeaky pop. You may also notice, if you watch really carefully, a flame shooting out of the end, but don't worry, you won't burn yourself. The test for chlorine is a bit more complicated, but if you suspect chlorine is being made, you take a piece of blue litmus paper. This is important, blue litmus paper, because you can get 2 types. You can also get red litmus paper, and we want blue. We add a small amount of water because we want to make it a little bit damp and a little bit moist, not too bad, not too much, and then we're going to hold it over the chlorine source. If we've got chlorine, our damp blue litmus paper will turn pink at first, and then it will turn colourless, and this is the effect of the chlorine slowly bleaching the paper, bleaching the colour out. The test for oxygen is we trap the gas inside a test tube again, and we light a glowing splint, but this time we blow it out, so just the tip is glowing. Okay, unlike in hydrogen where we leave it burning, with oxygen we blow it out and we leave the tip so it's glowing. Then you introduce the glowing splint into the test tube. If there's oxygen there, the tip will reignite, the glowing tip will reignite, so it bursts back into flames, and that is characteristic and proof of oxygen. No other gas will do that. So, summary time. A hypothesis is an idea about what may happen and why, and it's based on scientific ideas or observations we've already made. Risk assessment should cover the hazards and strategies to deal with them, and also it should be based around the equipment and the chemicals that we're using. The method for the required practical, today's required practical, is essentially the same as any electrolysis. There's nothing really special about it apart from the testing of the gases. Test for hydrogen is a squeaky pop test. Test for chlorine is it bleaches blue litmus paper, damp blue litmus paper. And the test for oxygen is it relights a glowing splint. Okay guys, I hope you found that useful. Please remember to hit subscribe if you've not done so already, and a like is also most appreciated. If you've got any questions, please let me know. I am due to be in school on Monday, so there's a slight chance I may be able to record some of these practicals if I'm not too busy, but I could well be very busy. So I'm not sure if I'll get the chance until after lockdown is ended. Anyway, I hope you and your families are all doing well and you're looking after yourselves and enjoying the sunshine that we seem to be getting right at the moment. Okay, take care, see you soon, keep studying hard, bye bye.